Okay, so Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome everyone. So today we'll start chapter 5. And although it's chapter 5, as you know, that as I just mentioned that um, uh, we will we decided to have it at the end of the semester. So we finished the discussion about the metals and the metal alloys, and to just to before the semester end, we said let's talk about the polymer structure. So today we'll talk about this chapter 5. We're going to talk about what is polymer, what different structure the polymer might have, and then also we'll be talking about also how can we create polymer, and then how to synthesize polymer, and then we will talk about the how can we measure the molecular weight of polymer, and then finally we'll be talking about different type of how we can classify different polymer according to their behavior when they are exposed to higher temperature. Okay, wonderful. So this is going to be the beginning of chapter 5, polymer structure, and hopefully you're going to enjoy it since it's the last chapter in this semester. Okay. Now, if you get here, the first question that we need to ask ourselves is, what is polymer, right? So basically, polymer, we can divide this word into two parts. The first one, poly, that mean many, and mer, that mean repeated units. So if you look at what's called polyethylene, maybe you heard this word many times, polyethylene. If you look around you, many the milk jug, and many plastics. Actually, it's called that's used as a container for carbonate for juices and for milk. It's made from polyethylene. So polyethylene, you have ethylene that's being repeated, right? So it's called polyethylene. So this is going to be the repeated units, right? So you can just have a bracket here and then you write N, and then that N could be 100, 200, 300, just telling you that this unit's been repeated 200 times, 300 times. So when you say polymer, so you have ethylene, and this one will have polyethylene because you have many repeated units of ethylene. Similarly, for a PVC, you have polyvinyl chloride, you have here HHH, and you have chloride over here. So this part will be repeated over and over throughout the chain of the polymer. So it's called polyvinyl chloride. Okay, and here propylene. So similarly here, this is the repeated unit that will be repeated over and over throughout the chain. So again, polymer mean many repeated units, many of the mer, and mer is the repeated units. Wonderful. So for the polymer, you have a naturally available polymer that we can get from the nature, like leather, silk, wool, cotton, rubber, like, and also we have some synthesized polymer, right? So if you look, as I mentioned, if you look around you, you're gonna find polymer has many applications that really help the humanity. And at the same time, there are some issues with some of these polymers, because some of them, they are actually harming the environment, as you cannot get rid of them after you use them for whatever application. So maybe you are familiar with, maybe during your life cycle, you will be in touch with one of these products here. I'm sure you've been through this during your early stage in your life. You got into this. You went you had to deal with these things over here, and then maybe you picked such colors when you were little, and then I think now you are using many of these products and polystyrene cups, shoes. And then you look at this one. This one actually, the Teflon. Maybe even people who did not get the chance to study material science, they might say this word Teflon, because this is the commercial name of one of the polymeric material fluorocarbon. It's called polytetrafluoroethylene. But when you look at this picture, actually, you can see metals. So the question is, where is the polytetrafluoroethylene is there? So polytetrafluoroethylene, what's called Teflon, actually, it is the coating on the metal. That coating that is so special, where if you have anything spilled on top of it, it will not stick into the surface. This is why if you go and buy a cheap type of coating, or let's say cheap product of pans, where you cook eggs, typically what's going to happen, the egg going to stick into the pan because the coating was not perfect. So if the coating done perfectly, what's going to happen is you're going to coat the metal, and that coating, polytetrafluoroethylene, has very low energy, surface energy, very low surface energy. So the carbon is very stable. So the polymer is very stable to be together, right? And if you remember, we say that the material is prepared to stay in the minimum state of energy. And because of their energy is very low, does not want to get into any reaction. So this is why they cannot get into any reaction. So this one, you have oil, egg, whatever, it will not stick into the surface. So now you can really appreciate the the polymer, how much they are really impacting our life. Imagine yourself, if you don't have such coating, how much time you need to wash the pans and the pots and the other things in the kitchen to get rid of those sticky things. And I'm sure now because the quarantine and because of the COVID-19, maybe because of the lockdown, I'm sure at least some of you been to the kitchen. I personally have done this. I'm doing this every day. You wash the pans and the other things, and maybe you cook. So every time you cook by now remember that this polymer is really everywhere in the kitchen, even the pan that you're going to use to make your egg in the breakfast. Okay, wonderful. So polymer around us everywhere, right? Okay, great. So the question is, what is the composition of this polymer? Well, polymer can have many different compositions, but if we want to talk about what is the main thing that exists in the polymer, well, we'll say that it's the most polymers, they are called hydrocarbons because they are made up of hydrogen and carbon. So in the backbone, mainly you have carbon, right? And with hydrogen. But this could be substituted by something else, which we're going to talk about, inshallah, in this lecture. Now, as you remember that carbon prefer to have to be bonded to four other atoms, because it has 8 electrons, and then it's going to keep 4 for itself, and then the other 4 electrons are available to be for bonding with other atoms. Now we can call polymers saturated hydrocarbons if the carbon is connected to four different atoms, right? So we have 1, 2, 3, 4. So 4 different atoms. We call this kind of hydrocarbon saturated carbon. So you don't have a double bonds, because if you have double bonds here, what's going to happen? You're going to reduce the number of atoms that the carbon is connected to. So this kind of hydrocarbon is called saturated, because here each carbon singly bonded to four other atoms. Okay, and we get into this famous times where, if you remember it, this is the composition and molecular structure for some of the paraffin compounds. And if you remember this one, methane, ethane, propane, butene, pentane, hexane. As you can see that As you go down in the table, you are increasing the number of carbon and also increasing the number of H of the hydrogen. In the same time, because you have more bonds, expecting the physical properties and also maybe the mechanical properties later going to be different. So this is why the boiling point is going to increase as you add more carbon and more hydrogen to the chain, molecular, to the molecule. Okay, so the other type is called unsaturated. So the first one is saturated hydrocarbons. We have carbon has a single bond here. It's connected to 4 different atoms. Double bond, the unsaturated hydrocarbons such as double bond and triple bonds. As you can see here, because of the double bonds over here, this carbon is connected to 1, 2, 3, right? So you have 3 different atoms. Similarly here, for the double bonds, for the triple bonds, you see that how many bonds we get? Well, you get only 1, right? 1, 2. That's only the number of atoms that the carbon is connected to. This is why this carbon is not saturated. It's called it's unsaturated hydrocarbons. Okay, wonderful. So now we will get into what's called isomerism. So isomerism is when you have 2 compounds, they have the same chemical formula, but they have different structure. So as you can see here, so this one has different structure compared with this one, right? So here all the carbon aligned in a single chain, right? Aligned in a horizontal chain, kind of horizontal. So but here you get some branches. So here it's aligned in a linear. It's better than the horizontal, because this is not, well, let me tell you something. So now the angle between these carbons are not as it's here. So there is some angles between these carbons, okay? But let me correct myself. So all the carbons here are not in horizontal, but rather they are in, it's better to say, in a single in a single line, chain line, okay? Here, however, you have some branches, right? So you get some branches out of the line of chain, right? Right? So this, so you have a line here, right? Here you get a line plus some branches getting outside of the chain. Okay, great. So so sometimes you have same composition, same compound, but they have different structures. Similar, if you remember, when we talk about polymorphism, we say that material can have the same material, same element might have more than one crystal structure. We call polymorphism. Here we say isomerism when we have a polymeric material that has the same composition, but they have different structure. So they have different structure. Now let's give a look into how can we move from ethylene, for example. So this is ethylene, right? How can we move from ethylene to polyethylene, right? Because this is a monomer, right? This is a monomer. This is the monomer that's not a repeated unit, only monomer. And then we're going to move from this point being a monomer to a polymer. طيب. So if you have one monomer, it's called monomer. If you have 2 monomers connected to each other, we call it dimer. And then if you have many, we call it polymer. Okay, great. So let's see how the reaction is going to happen. Well, first of all, if you consider monomer, ethylene monomer, طيب. So what's going to happen if this monomer react with a free radical? So this one has an extra electron over here. So free electron is better to say it. It has free electron over here, right? So that free electron, what's going to happen, that free electron will attack this carbon over here. And if you remember, this carbon has double bond over here. So that means it has 1 electron. So it's sharing its electron with this carbon. And also this carbon is sharing its electron with this carbon, right? So this bond over here is composed of two electrons, right? One belongs to this and the other one belongs to this, right? So what's going to happen once this radical attack this carbon will break this bond and will create a new bond over here, and that bond is composed of this, the carbon electron, and the free radical that was here, that has the free electron that was from the free radical, okay? Okay, wonderful. So that's called the initiation. So now the extra electron that you have here is gonna move outside, right? So as you can see it over here. So it's called free radical now. So now what's happening is you initiated the reaction. Now you have this free electron over here. What's going to happen now if this one see, as you can see, if this one see another monomer, what's going to happen? This free radical over here, or free electron, going to attack this carbon, right? And this carbon, we're going to break this bond to create the bond over here. So as you can see that, and this one, the electron here, the free electron will come to this end, and at the end of the day, you have this you have this part is connected to this part, and the free electron will come to this side. And now what you did, you form what's called dimer, right? So you have dimer. You have two mer, right? Two mer. So you have two mer. And if you continue the reaction, what's going to happen? Well, if you continue the reaction, you can imagine that you end up having a long chain of polymers, right? A long chain of polymer that has many repeated units, right? Now, I would like to point out there is a difference between monomer and the mer, right? So monomer, sorry, there is a difference between monomer and the repeated units. What's the difference here? So you notice here, this is the monomer. You start with a monomer that has double bond over here. But at the end of the day, the repeated unit, as you can see, does not have a double bond. So there's a difference between the monomer and the repeated unit. So you start with the monomer, you do some chemical reaction with the free radical, and then you end up creating the repeated unit, as you can see here. So this is the polyethylene. This is going to be the repeated unit that's going to be repeated over and over in the chain. Okay, so as I mentioned earlier, so the angle between this carbon actually is not as we saw earlier. So there is certain angle between them, but for simplicity, we draw it as a line over here. But actually, in reality, there is around 109 degree between each carbon, not 180. Okay. Now, what's special about polymer molecules that they really are gigantic molecules, because you can imagine you can get very long chains, and this is why they call, instead of call it molecule, they call it, sometimes they refer it as macromolecules. Macromolecules is referring that you have many molecules there. Okay, so within each molecule, actually macromolecules, because you have we have gigantic this molecule, because it might compose of many atoms that are connected to each other, right? So that makes it macromolecules. Okay, so the bonding between the carbon here, actually they are covalent type of bond. Okay, so the bonding between the carbon are covalent. And so this is a chain, this is a chain of polymer, as you can see here, right? So the bonding here is a covalent type of bonding. The covalent between the C and the H also is covalent type of bonding. But then the bonding between this chain and another chain will be typically van der Waals. Okay, and if you remember from the first chapter in the semester, we said that van der Waal is much weaker compared with the covalent bonding. Okay, so that means it's telling you that the bonds within the chain itself is very strong. However, between the chains, weaker. Okay, great. So here's the repeated unit. Now, so here's the repeated unit for some of the common polymeric material, as you say, polyethylene, PVC, PTFE, polytetrafluoroethylene. This is the Teflon one we talk about. So this is the repeated unit for the Teflon. So now you can go and talk with your families, show them the repeated unit for the for the magical coating that you have on the pans, and you show that this is what's different between polytetrafluoroethylene and polyethylene. Actually, in the polyethylene, you get hydrogen here. You get hydrogen, 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 and in the Teflon, actually, you replace this hydrogen with fluorine. As you can see, you have fluorine. So fluorine, when you do this, fluorine makes this compound at the end of the day has very lower surface energy, which make it more and more stable, so you cannot really get this kind of material into reaction. That's why nothing is sticking into the surface. Okay, great. So um, um, uh, what also would like to point out here is that, as you can see here, as you can see in this table, that um, uh, this kind of repeated unit, actually it has only two sides to it has two sides for reaction, right? It has two sides. However, this one is called trifunctional polymer because it has three different sides that are willing to get into reaction. So that's going to impact the way that the final structure of the polymer going to look like, because you have three sides here that might allow to create a network of polymer rather than chain linear chain of polymer. We're going to talk about this later, inshallah. Okay, great. But just I want to point out, see here they have two ends. However, here you have what is called trifunctional, because you get this three sides over here. Okay, great. Okay, now we're going to talk about the structure. Okay, so what we're going to talk about the structure, the molecular structure for polymer. This is very interesting because when you look at the structure of polymers, it looks like these chains they might interact with each other differently. So some material, some polymeric material, they have linear chain, and those linear chain actually they are weakly bonded to each other. So if you have a chain, so they are weakly bonded to each other. Some of them, no, there is a strong bonding between them. Some of them actually they do not exist in a linear chain. However, they exist in a network. So here you have a linear, and then you have a linear with some branches getting outside of this linear, and then here you get linear that is covalently bonded to another linear, and here you get the network. So I think by now you can imagine that you can guess that each one of these might have different physical and mechanical properties. Okay, great. So let's dig a little bit deeper. So if you look at the linear polymer, so if you look at the linear polymer over here, so what's happening is you get uh, uh, this single chain where the carbon in this chain is covalently bonded to another carbon. Sorry, the mer. So each green color over here is representing a mer. Okay, so each mer is covalently bonded to another mer, right? And then there's another chain over here which composed of mer, right? Because it's called polymer, right? It's composed of mer, and then each mer is covalently bonded to another mer. But at the same time, between these chain, you have secondary bonding, right? So as you can see, they have secondary bonding, which is van der Waal, right? So they still interact with each other, but the bonding is weaker compared with the compared with the covalent bond that exists within the chain itself, right? So the interaction between them is van der Waal. What does that mean? That means when you expose this material to heat, what's going to happen? You can easily break these bonds between the chains, and so these chains can move easily on top of each other, right? So this kind of polymer is easily to be formed in a certain shape because by applying heat, because you can make them much more softer. And actually, this one type of the what's called thermoplastic. So thermoplastic materials, when you expose to heat, it's going to become softer. And there are many examples of this kind of linear polymer, such as the high density polyethylene, PVC, polystyrene, and the rest. Okay. Now, what I want you to notice that because the chains are flexible to move, then you can efficiently back them, right? So you can efficiently back them. There is no restriction for backing them. This is why you get high density polyethylene. Now, let's imagine you have some restriction. If you remember when we say the covalent type of bonding has some restriction, the packing compare with when you have maybe other type of bonding. Because in covalent, the bond is with a certain angle, right? So it's kind of the same thing over here. When you have, let's say, a branched polymer, so you have a branched polymer. So if you get a branched polymer, what's going to happen? If you get branched polymer, you get this chain over here, right? And then in that chain, you have side branched getting outside of this chain. Now this might interact with this, right? So there might have been interaction between them, but this interaction will be also secondary bonding, not equivalent type of bonding. So these chains might interact with each other. But the main message here is this kind of interaction will result in a linear density polyethylene. Sorry, not linear. Sorry, low density polyethylene. So low density polyethylene, and the reason behind that, because here you have some restriction in packing these chains because of these branches over here, right? So you got low chain packing efficiency, and that will result in linear density polyethylene. Sorry, not linear again. Low density polyethylene compared with the linear polymer. This kind of polymer, actually they are branched, right? So in linear polymer, here linear polymer, you get high density, and in the branched polymer you get low density polyethylene. Okay, great. So now we move to another structure. It's called the molecule. It's called cross-linked polymers. And now in this one, what you have this chain, and this another chain, and this another chain. As you can notice that these chains are covalently bonded with each other. So you have some link. They are cross-linked with each other, as you can notice over here. So there is a covalent bonding between the mer itself in the chain, plus you have this chain actually is covalently bonded to this chain. You can imagine this kind of material going to be more stronger compared with the previous one, right? And actually this type of material is under what's called thermoset. So if the more that you heat the material, the more you heat up the material, the more you make it stronger rather than weaker, right? Rather than more softer, right? So you make it more harder. Okay. So why? Because cross-linking between these chains takes place during the synthesis at elevated temperature. So the more that you heat the material, the more that you're cross-linked those chains together to become more harder. So usually, okay, let me delay this later. We'll talk about the main difference between thermoset and thermoplastic. But finally, here you get what's called the network polymer. If you remember, we said that there are some trifunctional mer units, as I showed you earlier in the table. So you have three active covalent bonds. You have three active equivalent bonds that form three-dimensional network. So you can see that the final microstructure will not be linear. However, it's going to be like a network in a network structure. Okay, so they are heavily cross-linked polymers, and they are called network polymer. Okay, so before the actually this could be the topic. So after this topic, we're gonna have only one topic, and then we're gonna end. So we talk about molecular weight. So when we talk about the polymer in general, also we want like to calculate the molecular weight, right? And because all molecules are not in the same size, right? So we have small chain, long chain. How can you calculate the molecular weight of the polymer itself? So usually the way that we can do this, we use three different methods. The first one is called number average molecular weight, and there's something called weight average molecular weight, and the third one is called degree of polymerization. Okay, I'm gonna go in each slide to explain each one of these with example also. So the first one is called number average molecular weight, weight average molecular weight, and then degree of polymerization. Okay, and why we need this? Because if we want to calculate the molecular weight of polymer, what's happening is not all chains in polymer has the same length. So remember when we do initiation for the reaction and then propagation, so the chain become longer, right? So that reaction gonna continue. For some chains, that will continue further and further to become much longer chain compared with others, right? So at the end, the weight of this will be different than the weight of this. So we need to find a way that's going to consider the weight of all the chains regardless of their length, right? So the first one is called number average molecular weight. Number average molecular weight. So the way we do this is we say, okay, let's have. So we're going to use this equation, right? Xi is representing the fraction. It is representing the fraction of the. So what's going to happen? We're gonna spread them or sort them in ranges of weight, right? And then we're going to say how many. What is the fraction of the polymers that belong to that range? It's going to be clear with example, don't worry. So but at the end, the average number of molecular weight is going to depend on the summation of the fraction times the mean of the molecular weight of size range I, okay? And the other one is called weight average molecular weights. Let me give you an example. I think by example it's going to be much clearer. Okay, so let's imagine that the average mass of class, yani the weight of students in the class. What is the average weight of students in this class? And we want to calculate this by using the number average molecular, the number average, or we want to use the weight average. Okay, so let's try to see how can I calculate the number one, part A and part B. Now we have, let's say you have 10 students, and these are their weights, okay? These are their weights. Wonderful, right? So what we're gonna do, the first step is we're gonna sort them into ranges, right? So we're gonna say from this way to this way, it's gonna be one group. From this way to this way, it's gonna be another group, right? So we're gonna end up having something like this. So we're gonna group them, right? And then we're gonna see how many number of students in this range. So we got 2 students in this range, 2, 3, 0, 1, whatever, okay? And then the mean weight, what is the mean of this weight, right? So it's gonna be 110, 142, 184, okay. Now the difference between the way that we calculate the number average or weight average will be as follows. If you want to calculate the number average, you're going to calculate the xi, which is representing the fraction of this weight range, right? So the fraction here. How can calculate the fraction? Well, first we say how many students we get. The total NI is 10. So we have 10 students, right? This is going to be here in the denominator. And then here in the top, you have the NI, which is the number of students that belong to this group, 2. So that is representing the fraction. This is the way that you can calculate the fraction. The fraction at the end is going to be 2 over 10 is going to be 0.2. So 0.2 is the fraction. So that means 0.2 times 110 plus the weight fraction, so the fraction here times this, the fraction here times this, right? And we do the summation to calculate what's called the number average molecular weight. Okay. If you want to calculate the weight average molecular weight, so what's gonna do? We're gonna do the summation of we're gonna multiply Ni times Wi, which is the mean, and then we do the summation of this, and then at the end of the day, you get this, the summation gonna be in the denominator, and then in the top here, we're gonna get Ni times the Wi, Ni times the Wi, right? So this is called weight fraction. So this is called number, this is called the fraction, number fraction is called weight fraction, right? So as you can see that we get 0.117 for the first group, 0.117, that's going to be multiplied by 10, and you do the rest for the rest of the groups. So then what's going to happen is that you're going to take the first one, so the way that we can calculate the number average molecular weight is you do the fraction 0.2 that we just calculated, and you multiply 0.2 by the mean, which is 110, plus 0.2 times 142, and you do the summation to end up having 188 pounds. And then the similar for the average molecular weight. What's going to happen is you do the summation by multiplying the weight fraction times the mean fraction. Okay, great. So at the end, you're going to get, so almost I'm done. At the end, you're going to get two numbers. As you can see, these numbers are different from each other, right? So these two numbers are different. Although we are trying to calculate the molecular weight, but the numbers are different. We know that the numbers are going to be different because actually, if you look at this plot over here, the y-axis is showing the amount of polymer, and this one showing the molecular weight. Typically, the number average molecular weight is going to give you more. It's going to tell you more amount of polymer, but however, in terms of weight, this is going to usually this value is going to be higher. The weight average molecular weight is going to be will be higher. So the last part, the easiest part, just to very quick, is called degree of polymerization. So degree of polymerization is very simple. You say that it represents the average number of mer, which is the repeated units. How many repeated units I have, right? So the way that we can calculate this is we divide the average number molecular weight by the mass of each mer over here, right? The mass of each mer, right? So that's going to tell you the degree of polymerization. Degree of polymerization is how many mer you have in this chain or this polymer, right? Or the average number of repeated units. So for example, this one you have 6. 1, 2, 3, 4, 5, 6. So the degree of polymerization is 6. Quick example here. For example, the number average molecular weight of polystyrene is given. So this is the average number. This is going to be in the top here, right? So this one is given 500,000 gram per mole. Okay, great. And then the degree of polymerization, will be calculated by dividing this number by the weight of the molecular weight, M. Now, how can you calculate the molecular weight? You're going to look at the repeated units. How many carbons you have in each repeated unit? Well, you got 8 carbons plus 8 hydrogen. 8 times 12, because 12 is the atomic weight of carbon, plus 8 times the atomic weight of hydrogen. That's going to be 104. That's going to tell you the molecular weight of the polystyrene. If you divide these two, you end up having what's called degree of polymerization. So the degree of polymerization here is 4,800. Last thing here, you get what's called thermoplastic and thermosets. I tell my students thermoplastic is like the butter, and the thermoset is like the egg. So we have a butter. When you have a butter, the butter, what's going to happen if you heat it up? It's going to melt, can soften, right? So thermoplastic, when you heat it up, what's going to happen? They become more softer, right? However, thermosets, if you heat it up, become more stronger because you can cross-link between the chains. So when you divide thermosets and thermoplastic, we're dividing them the way that they interact with heat. When you expose them to heat, how they will behave accordingly. We can classify them into thermoplastic and the thermosets. So when temperature is raised, what's going to happen? The secondary bonds are broken. If you remember the linear polymer, the branched polymer, so we say the connection between the chains, actually they are secondary type of bonding. So what's going to happen if you heat them? You're going to break these bonds, which make them maybe more softer. So most of the linear and some branched polymer are actually thermoplastic. However, the last slide here I have is the thermosets. The thermosets, those kind of polymer, when you heat them up, actually you are non-reversibly harden those polymer, because you're going to create more and more cross-linking or cross-links between these polymers. So you make them more stick to each other, so become more harder. Okay, I think by this we end this what we need to know about chapter 5. Thank you so much for your listening. We're gonna go over this inshallah in the next lecture as a revision. Thank you so much.